Great. Yeah, then hello as well from me. My name is Wilbrandt. I'm from FZI Research Center for Information Technology in Karlsruhe, Germany. Maybe just a short overview. We are a research and transfer institution in Karlsruhe, Germany. We are a non-profit foundation closely associated with KIT there, the university. And we are around 250 researchers with only like a small department then focusing on robotics tasks. And we combine for our transfer projects both larger publicly funded projects as well as direct industry contracts. And yeah, we are long-time ROS user, long-time ROS industrial member. And in robotics, we are kind of working all over the place, so starting with 2D, 3D perception. We are looking at robust navigation, also in complex environments, field service robotics, but then also more related to this talk, more industrial use cases where we are looking, for example, at force-guided manipulation, assembly strategy, and yeah, different techniques for that. Through the, let's say, breadth of projects, I'd say we have some experience in integrating a lot of different hardware. With some projects, we just using different vendor components that we plug together on the ROS side, to having some custom or, let's say, changed components that we need to integrate to fully custom solutions. Today, I'll specifically talk about robot arms that we used. So we have 2 KUKA robot arms currently in the building. I'd quickly like to say this is not related with KUKA at all. This is just we had these robots, we needed to work with them. And the problem for KUKA arms and ROS-I, there is a ROS industrial driver actually for those. But that did not, and there are several ports of that for ROS-II. But there are several reasons why that did not really work for us in our use cases. So number one, we are looking at an assembly use case where we want to integrate this with other robot arms and a lot of sensors, actuators, and all that. And with like the normal KUKA arm, like I think with many ROS drivers, there's no further integration there. Like you can control the robot, but all the other features that the arm might have in that regard, you kind of out of luck and need to do that all yourself. On the other hand, we have a like robot machining application, and here we have very, very long trajectories, so might be a single trajectory of like 15 minutes, which I think is pretty uncommon for ROS use cases. But also we really care about smooth velocity profiles, smoothness in the execution, and robustness to jitter as well. And so because of that, we build up a driver for those, and I think some of those techniques might be of interest also in other people, and I think there are quite some people here who are interested in robust driver integration, so I thought this might be a good opportunity. So I first give a very short introduction to RSI and how this works. This is not the focus here, but I think that's kind of required for the things to come. And then I'd like to talk about 3 topics. One is asynchronous control and how we achieve that here in a robust way. One is integration of additional components, basically using all that the controller has to offer for us. And finally, some software architecture points, also maybe a little bit broader, what we have seen with other drivers, for example, where we've had problems with integration. So, as I said, very short introduction. How does communication work on the KUKA robot? We have our controller and we have our ROS PC, obviously. We have some configuration files we need, and as soon as we start a program, the robot will start sending us XML files, giving us the current state of the robot at 250 Hertz. And we are expected to return on the same connection, basically, another XML file which tells the robot where to move. And this is probably what Felix also mentioned, like this is very much we send every single waypoint. The robot tries to follow that as closely as possible, no further handling on the robot controller side. And for that, we kind of need 3 pieces of configuration. One is the RSI configuration, where we tell it which information we want to send. So for example, here we not only send robot positions, but also the estimated joint torques. They are not great, like basically a factor on the motor currents. But we tell it basically how the signals should flow on the driver. We then have an XML file that tells us how these signals translate into tags in the XML. And finally, we have a program that we need to execute on the robot to start the communication. And just to say this, like, you don't really need to configure this yourself. This is all also part of the driver, like if you just want to move the robot. And I think that's enough for now for how this works. So asynchronous control. If you normally integrate a driver in ROS-2, I'd guess good way to go is ROS-2 control, where we have this very fixed cycle. We have a read from the hardware, we update all our controllers, and then in the write, we should write the new commands back. And on first glance, that looks kind of very, like it matches very well to this protocol. So in the read, we basically read the last package that came in. We update, we pass that, get all our robot state, update the controllers, and then in the write, basically send back the current command. And we can do that for some cycles, but there is, and this is also how many drivers work and also how the previous driver worked. The problem we've seen here is, number one, the control period here changes based on the delay. So you might have the ROS control cycle basically getting quicker to the read and then having to wait for a packet to come in. And this might not be a big problem in some applications. In other ones, this, especially if you combine this multiple drivers that expect to always be able to wait here and delay everything, this means you also throw off the next driver's timing. So this kind of a cascading effect. And also, the delay basically between the state we get and the command we send also changes based on the, let's call it, phase difference between our control cycles. And in particular, what we saw here was that when we, for example, send a velocity with a fixed velocity command, basically increasing the position command every step, this means that when the period here changes, that what the robot sees are actually deviations in the velocity it tries to control. And that, in turn, means we were never really able to control the robot at anywhere close to its full speed, which might be nice to do. So very easy and probably obvious answer to that, we just move this all to a separate thread, have some synchronization buffer in between, and every time something comes in, we just write this to this buffer. We take the last command from the buffer and send it out, and the same, basically the same happening on both sides. And this mostly works, I think. Also, this is how many drivers are then structured. And in particular, we don't have this delay problem anymore. Like all the reads and writes take a deterministic amount of time. This is great. But if we take a look at this case here in the bottom, there's actually a problem here. So here in the read, twice we will get the same state from the robot. So depending on how the clocks between the different robots shift against each other, we might have basically either double state in 2 cycles, we might skip a state, and the same obviously also for commands. And this, in this case, is a real problem. So when we look at the commands that are sent to the robot, this looks kind of nice, but if we look at the derivative of that, there are all these spikes, and I was not sure about the audio, we have videos of that. That sounds really bad when you execute it on the robot, and is probably not great for it. And in particular here, this is exactly what we would expect. So we send our kind of target velocity, then it goes to one point of 0 velocity, then double that velocity, and then back again. This is bad, and this, we need to fix this. And one step further, if we now look into this, here I've plotted in blue the period, so the time between 2 writes we have to the robot, which is great, like 250 hertz, this is 4 milliseconds, this is exactly as it should be. But then in orange, we can see the time between when a packet comes in since the last write. And here we can see exactly that problem. So our phases shift against each other, and because of jitter on both sides, we will have these transition periods where we have exactly this problem of missing a packet, getting 2 packets, all that. And here, this is around 550 seconds between this. So this is on the millihertz range. This is a very small shift, but is a real problem for our control. And yeah, one way would be, hey, this is not really worth it. We go back to basically sleeping on that. Here we took an approach that I've not yet really seen anywhere else. And that is we explicitly measure this phase shift. Because we have all the information in the driver. This is exactly information from the driver, so we can try to estimate that and based on that, correct the command that we send to the robot. How does this look like? So we've added another component here, our command interpolation. And basically, I'll jump straight to the second one because we are now looking at multiple commands. When our package from the robot comes in, we basically keep our buffer of the last 3 commands. And we can now take a look at the time since the last write command and the time since the last message from the robot. So in this case, we can see that the write is very quickly before that. And on the other hand, the last message is significantly longer time ago. And this is all we need to get our relative phase, so to say. And then basically do linear interpolation between the output, the commands we wrote. So here, what we send back will be based on this, let's say 20% or something. We just interpolate between our last commands and send that out. This has some really nice properties that. So if we miss a packet, this perfectly corrects it. If we get 2 packets, this corrects it. So in, let's say, here, for example, we get our packet, and we have had 2 writes since the last packet. Because just the way that these are then added into this buffer, basically here we have 2 new commands in the buffer, and then a very low phase. This corrects for it correctly, and yeah, this worked out quite nicely. Some notes on that. So for us, it worked. I have some videos proving that probably. But this is obviously a big implementation effort and might not be relevant for all hardware or for all applications. So maybe just some framing here. So for some hardware, this is not really relevant. So if you do a lot of processing on the robot controller itself, like I'd guess, for example, with movement primitives or doing spline interpolation on the robot, then you don't really have these problems when you send 2 commands consecutively and can handle all that. Also, in some application, blocking might be not that big of a problem, but I'd also say this might not be a problem if you only use your hardware, but if you then try to integrate it with other hardware, this will become a problem. So for example, we've had robot hands that had a blocking read in their read function, and then basically limiting all of our robot to 30 Hertz, and it really didn't like that. So that should be considered. Also something that happened since then, so ROS control now actually supports asynchronous hardware interfaces. And this is probably a good solution to this. So what this does is it decouples different hardware interfaces to each run in their own thread. I'd say for most applications, this is probably a good solution. And there are then some edge cases where this doesn't work out. So for example, if you have multiple components that you want to control in unison, then you still have exactly this problem, because at some point you need to synchronize between them. But in general, if you just want to have, for example, multiple robots working on their own, then this should probably be the solution. Yeah, and as I said, this is significant implementation effort, so that should probably also be considered when thinking about this. And just, yeah, I mean, this really works. This is not that impressive to see on a video always, but we actually got our KR50 to run at around 70% velocity. I think 80, 90 was still pretty stable. This is controlled, like the normal ROS manipulation pipeline, I'd say, is move it, going through some controller to the robot. Here we are mostly then limited by, yeah, this basically move it, timing the trajectory according to some maximum accelerations, which is not a thing. So all of these robots have a torque limit, not really an acceleration limit. So it is kind of hard to say to specify some acceleration limits where you still get good performance, but also don't constantly run into torque limits. Yeah, But that said, this works. We have that on the driver. We've used it successfully now for a while. So I'd say that's good. Let's continue. Next point, component integration. And here I want to make maybe a short comparison between some of the research hardware we are working with versus the more industrial use cases. So on our research platforms, so for example here with our legged robot Lauron, we are very happy to have specialized hardware where we need to write drivers for every single bit of that. It's more important that they have some very good performance metric in one regard than it is that it's really robust or that it's really easy to integrate. And normally here we are totally fine with running that on our control PC because, I mean, how long will this run? For a few hours, for, in a good case, maybe a day. But we also don't, like, we are totally fine with running this on a normal Linux PC, maybe with some real-time patches, and then writing a lot of driver code and working with that. In an industrial use case, I don't think that's really the way to go. So if we have a larger assembly cell, we don't want to write code for every new piece of I/O that we want to integrate or for every new single sensor we add. And this is also where probably a sentiment that will be heard throughout the whole week. Industrial automation is way better in some cases than the ROS side because there are nice interfaces to use. So if we use EtherCAT, we have ESI files and controllers basically know how to handle them. We have that for CAN-open with EDS files, IO-link description files. And also this is really robust and real-time safe. And yeah, maybe most importantly for this talk, this is already on our robot controller. So even if we don't want to integrate an extra PLC or something, we should just be able to use all of this to our advantage. And we kind of did that in our driver by, yeah, basically using the controller as our hub for extra components. So goals here, we don't want to write extra drivers for the, let's call it, simpler components. We don't want to write all the communication layers for those. And we want the real-time communication to be handled actually in real time on the controller. And just a short example here I'll give with a force torque sensor that we attached with EtherCAT because this is attached to the robot. This sensor would be able to run at much higher frequencies, but I mean for robot control, we don't really care if we run at exactly the robot rate. And the nice thing here on the robot side, we do it as in, let's say, traditional automation we would. We just import the ESI file that's provided by the vendor into the KUKA software. We can see the signals and can map them directly in. Here we even do the, let's say, the unit conversions that we are in nice ROS units, so newtons, newton meters, seconds. And then basically all we need to do to integrate the sensor is to pass our signals into our RSI object, then tell our Ethernet config that we had in the beginning that these signals should also be transmitted as part of RSI. And finally, here we even went a step further. This would not be necessary for something like an I/O, but for example here, when starting the program, this will read out the conversion rates and stuff like that from the sensor. And this is all completely done on the robot side. And on the ROS side, we don't really need to change anything. All we need to do is in the URDF, tell the driver that we have these signals now. So we have here in a pass-through sensor element, we tell it how the signals are named in the RSI communication. And even here we have some offset here. And this is then read by the driver on startup. It will now know to pass these elements out when it receives state, and also this works the other way around. And I mean, obviously we'd have 6 state interfaces here, but I think this is much more realistic for, let's say, more complex integrations. And here's an example of that. So with only that done, we can now use all the things that are really nice about ROS. So here we have move it, planning a motion, creating a joint trajectory from that, and then actually using an admittance controller based on that force torque sensor. Once again, this doesn't look too impressive because it's basically only going down, but compared to not using the force torque sensor, it's not no longer breaking our screwdriver, so I guess that's pretty good. And we've kind of done that in one cell a little bit more excessive. So obviously we have the robot controlled again through ROS. But then we also have I/O terminals attached to it, for example, to control a quick change adapter and the sensors from it. We have another I/O terminal somewhere that can control the screwdriver, and then also here going over different field buses, an adapter to an I/O link device that then controls our gripper. So I think doing this purely by writing ROS drivers would be a lot of effort and probably not that well spent time. Yeah, so I think that's it for component integration. Finally, I want to talk a little bit about software architecture. I'm aware like these are just maybe points we saw during development and also looking at other drivers. We are obviously not the experts for writing production-grade real-time software, but I think these are some things that might be very relevant when designing ROS drivers or ROS controllers. So again, remembering back to our ROS control cycle, we have our read, update, write loop running at our fixed frequency. And the goal here, I think, always is to reduce the jitter in our execution time here. If possible, this read and write should always take the exact same amount of time. And as I said, this is important even more if we have multiple interfaces. So 3 things I want to talk about. Data structures, and I think here the main thing I can say is you should probably not write those from scratch. It's pretty hard to do, but here, for example, we made extensive use of boost lock-free, but this is also now integrated in real-time tools, so there are a lot of good synchronization and multi-threading library tools in there, and very easy to use and integrate into ROS2. Then next step, implementation. I think there are some pretty obvious parts. If I didn't say that enough already, we should probably not do blocking IOs in our drivers. But what I also want to say quickly, we should consider transitions. And then finally, I'll talk a bit about allocations and how those can affect the software design. I talk about lifecycle transitions, and this is mostly maybe some issues or misconceptions I've seen when interfacing with different hardware that kind of made them put out or just generally made problems. So if you've not seen this, I mean, basically this is a small part of our life cycle, but hardware can then be unconfigured, inactive, or active. And for many drivers, I've seen that you only really consider this active case. And that does not quite match up with how that's specified in ROS control. So there it is the expectation kind of that you can already do reads in the inactive state, and these will get called. And you should be able to provide states. If you're not, that's not a big deal. But it's kind of like you should be aware of this and not basically send out garbage if you haven't set up the robot correctly. And one, let's say, really like a direct consequence of this is that the on-activate and on-deactivate will happen as part of your real-time control loop. And what I've actually seen from a lot of drivers is that they will use this to, for example, set up all their networking, configure their hardware, stuff that takes a while. And if you have multiple hardware components running, then this will just, basically stop breaking the others completely out of their control cycle. And this has actually been a problem with some hardware for us. And ideally, it's not that hard to just check this out. So also, during preparation for this talk, I've seen a problem on that with the KUKA driver, so probably have some small adjustments to do, but it's pretty easy to check this out. This becomes even more relevant when, for example, designing end effectors where it might be very valid to basically completely shut down the driver and disconnect it physically from the robot, but expect it to be able to come up later on again. And then I'd quickly like to talk about memory allocations. I think there that's pretty easy. Like, you are able to pre-allocate most of the things you need in a driver, latest in our on-init or on-configure when we already know our complete robot model. Can become a little bit more complicated. So, for example, in the different buffers I had in my driver architecture, you can kind of lose track exactly of how many, for example, RSI states you need to keep in flight. But I thought this was quite nice. You can still have some upper bounds on the elements you have. So, for example, just keeping a cyclic buffer. Pre-allocate this as you would with other information in the driver, and basically keep track of the numbers you've handed out. A very easy way I found is to just keep shared pointers to these objects and basically always give out the next one, see if somebody is still using it. If yes, there has been an overflow and probably some timing issue in your driver. The other thing about memory allocations is that it's really hard to judge them manually. So it is very hard to see how much you allocate as part of the control by just looking at the code. But there is a lot of tooling for that. So, for example, Wilbrandt has this massive, I don't know how it's actually pronounced, but analyzer, but also there's heap track, which should be a lot faster, at least in my tries. And all you need to do is add this in a launch file, for example, as a prefix. At that point, it will keep track of all allocation calls in your code, and you are able to later on analyze these. And this can incur significant slowdown. What I found here, so as part of the driver, we also have a small simulator for the RSI traffic. It's not that complicated to write that in Python. I think for many of the protocols we use when connecting to ROS, or even if you have something more elaborate like for UR, the UR-sim or something, then this is very, very valuable to have. And one example here, so we care basically about three functions: our read-write functions and the run function of our communication thread. So if we take a look here, this is a trace over like 10 minutes. In our read function, we don't get any allocations in those. That's great. We then take a look at our write function, and here we have 183, I think. And this is a little bit weird because you expect these to either be a very large number or a very low number. I think the issue here is with a debug call I have in there about basically when the driver is not keeping up, and ROS will then do some pre-allocations for that. I think there has been some discussion in ROS control about suitability of normal ROS logging for these real-time contexts, but I can pretty safely say like this is not happening every cycle, and this doesn't happen after the first cycles. So I'd call this good for now. And then finally, in our communication thread, here we can see an example where this doesn't work out. So we have around 2 million allocations. And this now really helps because I can take a look where exactly this happened. This was in our XML parser. And this is then very easy to fix. This has been fixed since then. And since then, there's no more allocation there. Great. And with that, I mean, this all works quite nicely, I'd say. We've integrated that with a different robot, with all the hardware we've seen earlier. And this, I think, works out quite nicely. And these are also techniques we try to use now for when we need to integrate other hardware. And if you've not seen this and thinking, hey, how does this work with tool changers? This is not pretty hard in ROS. Then I'll talk about that on Wednesday. So small teaser here. And with that, the short wrap-up. So this is all open source on GitHub. Here on right, you see maybe because of one limitation. As I said, we are not really associated with KUKA, so we can't really share meshes for all their robots. Those are not ours, but the KUKA experimental driver has models for a lot of robot arms, and there are multiple forks, for example, also from Be Robotized, and we can use those directly. So this is from our execution tests we have in the CI there. With that, this is again the link to the repo, and I'm open for questions and looking forward to discussions in the break. Thank you.